And I apologize, I just noticed whatever I recorded up till this point was muted, so no voice until now. Oops. So, point is, we're going to look at solid waste. How do we handle that? And what do we do about that? Okay, first the concerns, right? Safety is kind of one of the major ones. That's pathogen related. And this is true if we're using animal waste, human waste, whatever. Of course, human waste is going to be the top concern. It's most likely to have human pathogens. So pathogen reduction is important for whatever we're going to do with it. So ideally, if we're going to compost some waste, the plan is to then use it for some beneficial use, which means some sort of agriculture, land application, going to mix it in with the soil, improve the nutrients, give plants more of what they need to grow, and grow faster, stronger, healthier, more fruit, all that. So that's kind of the thoughts. So pathogen reduction, because if we're putting this on the land and then growing something we're going to eat, well, there's some obvious concerns about pathogens getting on what we want to eat. Of course, you know, some things might be cooked, some things might, like let's say a coconut, it's going to grow in this nice shell. It's probably never exposed to that. There may be some questions. Certain plants might have some pathogen transport with the water that they're pulling in. Probably not, but that's still something to think about, at least in terms of chemical contaminants or metals, right? So there are some thoughts there, probably not so much pathogens if you're consuming something like that. There's a rule of thumb if you're visiting somewhere that doesn't have good control of hygiene. They say if you're going to eat produce, it needs to be either cooked, or you peeled it yourself, or you just throw it away, right? And so the condition in Nicaragua wasn't too bad. I will say that every time I go, by the end of the week, my stomach's a little iffy, typically. Not a lot, just a little bit, and then maybe for another week, and then I'm approximately better after that. Something like that. So I don't know if that's your experience or not. I went ahead and ate some lettuce and things in the facility that like hosts us. They have better education in general, but we also went downtown and ate at a restaurant or ate different places, and you know, that's a risk, right? So if any of you have anything severe, hopefully not. Kind of did. Oh no. Oh no. Oh no.
Up till 8:30 a.m.
Oh no. Okay, so we did have some food infection then, probably. Sorry to hear that. But the food was good, right? Yeah. So no help in the senior design category there, though. forgot to warn you. Yeah. So there's some concerns, right? Yeah. It's just the whole control over those systems is not quite there in place. So certainly something that can happen, and that's, you know, I would say whatever I've typically experienced is pretty low grade. I also typically will avoid their ice and things like that. Maybe it's not as big of an issue these days, but still the produce and things, you know, even if they're not composting and using biosolids, there's a good chance hygiene practices are not necessarily in place, right? So you probably got a feel for that. You don't know who's collecting the produce from the farm. You don't know if they know anything about hygiene. You know, so there's some risks there. But feeling better now, I hope? Good. Okay, so those are the concerns, and anybody handling these things, obviously they're a concern as well. And in fact, even in the States, we have, when we do land application of biosolids, they're generating lots and lots of biosolids and sometimes applying these in like spray trucks. There's some concerns for aerosolizing nasty stuff that hasn't fully been degraded, processed properly, and that for those workers, that's a concern as well. Okay, but the utility for doing any sort of composting would be getting fertilizer, the nitrogen, phosphorus, and potassium especially, but also soil texture in terms of the consistency, how much water can it hold, retain, or drain. If you were to dig in Louisiana, dig a ditch and try to grow something in the dirt there, well, you might have an issue that the soil is not draining enough. If you do the same thing in Nicaragua, where it's all this volcanic, a lot of places it was this very nice soil that just drains really well. It's almost like sand. Well, if it doesn't hold any water, it's just going to dry up immediately, right? So adding in some organic materials can actually shift that in either direction beneficially, to give it a little more drainability or to hold a little more, kind of depending on what the soil needs. So that's pretty helpful. Utility of simply having a place for this waste to go rather than just dumping it somewhere. If you're going to be real fancy, this is more kind of an industrial scale. You can generate biogas by the digestion process. You'll form a bunch of methane and can overall, no matter which way you're going, you can potentially recover some cost here. So if you were going to pay for fertilizer, but you can use some sort of biosolid compost, that saves cost. If you had to landfill it, then you'd be recovering that cost instead of landfilling it. Maybe you can even sell it, right? So there's all those are the reasons, pretty obvious, but I just wanted to put them there as why we would care about it. So yeah, so basically I'm taking some material that is kind of at the industrial scale and then talking about it, what that would look like at a more developing scale and how these may relate. Okay, so a formal definition here for biosolids composting. This would be aerobic, thermophilic, meaning temperature loving, right? That's the root of it. Means high temperature bacteria that can handle high temperature. Decomposition of organic constituents to a relatively stable humus-like material. So soil-like, basically. Humic acid is just organics that come from soils, is what we say. So humic substances, humus, just essentially converting the biosolids into something that's textured like a soil. And so you have to get a lot of water driven off. You have to give the bacteria and other organisms lots of time to munch on stuff and to produce. You'll end up with the soil-like material. And you're going to do that giving it air, giving it some aeration. It's obviously going to be a lot of pockets where there's not so much air, but in general, you want to stir it occasionally. You want to do something to provide that oxygen so that it's not all anaerobic. If it was all anaerobic, you'd probably have temperature run out of control, just the way the biochemistry works, and then the bacteria making stuff that's sort of reactive, and you can actually get out of control temperature situations if you're not careful with your composting. Okay, so then the factors that need to be controlled, the moisture, so then pH and temperature, oxygen concentration, the microbial community. Controlling these other factors should control that, but that's part of why we control them, is to get the right types of microbes growing and processing all of this for what needs to happen. And then also the material type. If you just had a bunch of like tissue for a tissue recycling plant, and that's all it was, that's mostly carbon. You'd have a hard time doing composting because there's not really the right nutrients. Or if you just had an extreme excess of nitrogen, maybe you're going to get a lot of ammonia, and then it might poison the process or something. So you have to have some material that's compostable, right? You can't do 100% coffee grounds, probably. So if you've ever done any at-home composting, it's kind of the same principles, just in a very micro scale there. So this is maybe what it would look like when you apply it to land here, where you'd have rows and you'd kind of till in that compost or add it on top, but probably mix it with the soil there. I mentioned a lot of these already, but there's just kind of a nice list for you. You're recycling it, reducing dependence on chemical fertilizers. So that's a big one for organic farms. So the photos we showed for that farming in Nicaragua, Their premise there, by the way, is to do organic farming and sell, in that case it was turmeric, to, I think it's Gaia Pharmaceuticals or Nutraceuticals, whatever the company's name is, so that they can make these energy shots or health shots and other products like that. And so they're making this organically, meaning they're trying not to have any pesticides, insecticides, herbicides, any of that. And also, I think they're trying to go without any chemical fertilizers. I don't think that part's necessary for organic certification. I don't actually remember, but it might be. But at least the other, like the pesticides, are a no-go. But their thing is they want to do this all natural and grow a good product, and harvest that, and be able to sell it. And the neat thing for them in terms of economic development is they are teaching the locals how to do that in a way where they can get a much more profitable crop to sell. Because a lot of farmers down there will simply grow rice or beans, maybe corn, so a lot of these staples, and if they have a good year, they're just doing a little better than breaking even. It's not a lot of profit margin there. It's more like subsistence, just carrying things on, getting by. Whereas if they can change their practices a little bit, they could potentially sell for a lot bigger of a profit and improve their lives accordingly, and provide a good service, good product for people who want it, right? Maybe we want these little health shots. Don't think it would fix the GI issues, but maybe it would help with preventing a cold or something, right? Okay, so that's sort of on their radar and why they're interested in this. Okay, so offset of use of natural resources. It's kind of repetitive here. There's also a bunch of micronutrients that the plants may need or may benefit from having some extra. So things we might not think about that just need trace amounts. Well, in the organic matter, is probably replenishing that pretty well. Sometimes this will just simply make the plants grow healthier and therefore have their own defenses in place a little better against insects and things like that. Talked about the water holding, the aeration drainage, permeability. So all of those could also help with the plant roots doing better, healthier, all of that. Okay. Some disadvantages. I talked about spraying this stuff on. You can see a couple trucks here doing just that. Does not look so attractive, and you definitely wouldn't want to be in that vicinity, I would expect. So we've got odor, we've got potential survival of pathogens in the product, and then if you're dispersing them, there's some serious concerns about either aerosolizing some of these fungi and things. We know a fair bit about like how bad mold is in the indoor context. Well, are we doing the same thing and then spraying it around? That could be a hazard for anybody in the vicinity. Another potential issue is sometimes you'll have a lack of consistency in what you make, right? You're trying to make a compost that is usable and that you could use in this field and in that field, and you kind of know what to expect. But one day your moisture content might be a bit different and your pH might have gone differently based on what you added. So some challenges there. If we're composting municipal wastewater, there's also a significant importance to check on the metals and to monitor them. Trace amounts of heavy metals applied to a field like this once would not necessarily be a problem. Again, I said trace, right? There are some plants maybe you would take it up very strongly, so that might be an issue. For example, one of the reasons tobacco products are such a hazard in general is because they're really effective at extracting heavy metals, trace them out. So they'll even grab radionuclides and concentrate them into the tobacco plant. So we can use tobacco plants as a remediation tool, but that also means if you're ever using a tobacco product, you've just concentrated some bad stuff and you're exposing yourself to that. So in addition to the obvious issues with smoke inhalation and incomplete combustion products and all that, there's also that factor. Okay, so long term, if we're doing this more industrial scale land application, we do monitor, okay, what are the amounts of heavy metals in this, and what's the total in the lifetime of applying to a particular plot of land, what's the total amount of metals at some threshold we say, okay, no more, we cannot apply biosolids here anymore. We're just done, to avoid potential issues with health risks associated with that. Okay, so as we look at composting techniques, there's really two classes of biosolids we would specify. Class A being the high quality and Class B being not as high quality. The difference here is really the level of pathogen treatment. So how appropriate is it for spreading around in areas where humans might come in contact with it? Now, none of it's good for like direct human contact. We try to avoid that, but Class A, they have this high standard, and it's okay if you were to apply this, let's say, in an area where the public may come in contact with it. I'm getting a lot of messages, and I'm now getting a phone call. Let me, this is about a proposal that's due, so pardon me just a second. Hey, Kevin. Hey, I'm teaching a class. Can I call you back in a half hour, or do you need it now? You need to talk now. Okay. Okay, you want me to call him now, or do you want me to, I can send you his number. Okay, all right, and I'll check back with you in about half an hour. Yeah, and I'll send it now, thanks. Sorry, speaking of a crazy week, we've got a big proposal due today, and Kevin's actually calling me from England, so. You guys feel free to interrupt. I'm interrupting too. If you had something you need to start. Okay. I'm so sorry about that. Would not normally interrupt class for that. Okay, so crisis hopefully averted. Class B biosolids would be treated a bit, and so we expect they're not going to be a huge hazard, but we have a little bit of limitations for how directly humans would come in contact with them. So these would probably not be approved for, let's say, a spinach farming, whereas Class A might be, because we expect to just take that spinach and then wash it and process it from there. So it's a very direct exposure that's going to be growing in the soil. It's going to be touching the pathogens, all that. So that's the difference between Class A and Class B generally. So the technical difference here then, Class A, we basically have a standard where we have to get it to a high enough temperature that should kill most all the pathogens, or at least enough of them where we have much fewer issues, and that would be to get a temperature of 55 Celsius for at least 3 days in like, let's say if we were doing some sort of pile. The temperature, by the way, is largely just a biological activity function. If you have a lot of biological activity, a lot of microbial action, they're going to raise the temperature kind of themselves. And so at some point they'll get themselves hot enough if you provide the right conditions. Now the class B, you have to reach that 55 Celsius. I'm sorry. So there's two ways to get the class A. One would be that aerated static pile or some sort of in-vessel. I'll show you some pictures of that in a moment. You get all that, the biosolids in one spot, and you're blowing air through them one way or the other. So the 3 days is one version, or you hit 55 degrees Celsius for at least 15 days if you're just turning this sometimes. Because that's like one spot you're measuring the temperature. You just have to confirm that it's got up to that point. Maybe not the whole pile got up to that point, but you turn it 5 times in that 15 days and you call it good. So it's just a little simpler operation, and so it takes a little more time to make sure everything's got a good. So that's how they regulate it. Class B is 40 Celsius or higher for 5 days during which the temperature exceeded 55 Celsius for at least 4 hours. So for any of you who were doing some of that fecal coliform testing in the field or have done any microbial analysis, one thing I'll note is that anytime I've worked with E. coli in particular, if we get them up to even just 50 Celsius, they die off in seconds. So they're very unhappy if you get them to 50 Celsius. Now maybe they could repair that if it's just a short thing and then they're fine, but there are other pathogens, other organisms that would be more resistant. So this is why we want to try to get it up pretty hot. And if you stop and think about it for a moment, our body temperature is 37 Celsius. So that means like a high fever. So in Fahrenheit, that it's 97.8 or whatever, right? So in Fahrenheit, we would call a high fever like really dangerous if we get up to 105, right? That's like real danger territory. So if we imagine that in Celsius, that would put us at something like 42, right? Is super danger zone. So if we're pushing these to 45, we can't survive that. If our internal body temperature got to that, we can experience that in the environment and be fine. We'll be sweating a lot and all of that, but we would survive because our internal body. So that's kind of one way to think about it. You're almost getting to the point where you're scalding them at 55. It's not boiling by any means, but if you keep them there for a long time, a lot of them will die off. Okay, so then, this class B, you have to have them kind of hot, but they're fine at 40 for the most part. You also have to have gotten them to a pretty good hot temperature for at least a few hours. Okay, so I mentioned metals. Here's a list of the types we'd be looking at. You'd have some ceiling concentration where you say anything above this is no good. And this is milligrams of this metal per kilogram of the biosolids. So there's a couple ways we could establish them. I think the ceiling is, this is referring to you can never go above this amount on the field, in total, something like that. So we could look at all these. Of course, we don't want any of them, but some of them, like zinc, is not such a big deal, right? We can have a fair bit of that. Okay, so to process the wastewater, or the waste solids, to do the composting, what we need to do first is dewater, and if necessary, add some bulking agent. So while we were in Nicaragua, a few of us were talking with John Bland, kind of the former director there and the founder of the organization. He was talking about what they did to compost, and there's a few different things they were doing. One of them was taking waste from a chicken coop, and I think they were mixing that in with, anybody remember, maybe that was the wood chips or something. Another version was they'd have a pig farm, and they'd have all the pigs being raised, and the material, what they did was, instead of just letting the pigs, they're gonna make a mess wherever they are, basically. And to help with that mess, they put in a lot of corn husks, just like, I think, chopped up corn husks, like chunks of corn husks, just everywhere in the pigsty area. And so as the pigs make their mess and everything, those do a pretty good job absorbing it and collecting all the nutrients from the waste material. And giving something for that waste material to kind of collect on, kind of like cat litter, right? So it's like putting an organic version of cat litter all through this thing to catch everything, and then every so often they essentially harvest all of that, and then they compost that. And so a bulking agent, whether it's used during the process or if you add it later, would be a way to give the compost some more material structure rather than being like just a straight soup, right? To give it something else to have a bit of airflow and all that. So it could be sawdust, could be chunks of corn husks, could be coconut shells, things like that. Lots of different things could be added, and that would improve that porosity, give you some more moisture control, things like that. Okay, so in wastewater treatment proper, we typically would take our solids and then send it through some sort of belt press to squeeze out some of the water. That'll do two things for us. One, prepare it for biosolids processing if needed, or if that's going to be a thing. And two, make it cheaper to transport, right? Water is heavy, it costs a lot to transport it, so whether you're taking this biosolids to the next process or you're landfilling it, you want to get rid of as much water as you can. So you'll be dewatering it kind of regardless in most processes. Okay, so then you get that temperature target between 55 and 65. That's the pathogen control, and will help you evaporate a fair bit of water as well. Then at some point you want to stabilize it, let it cool off a bit, and let the microbes continue their work at a lower temperature, do additional drying if needed, and sometimes you might be able to or have a desire to separate that bulking agent. So maybe you're sifting through it at that point. Okay, a moisture content, we have some targets. You need at least 12 to 15% for any real biological activity. So if it's too dry, it's not really going to work. You can imagine trying to compost something and it's just all dried out. You're not really going to get any bacterial action, right? There's a reason we have dried meats and things that are preserved, right? Bacteria like moisture. If you have less water content than 40%, you may have a condition where you're inhibiting growth a bit. So you actually really want 50 to 60% moisture content. If you get any more than that, you're generally getting too muddy. And then it's too soupy. So we could take a look at a graph where we have some mixing ratio, how much wood chips volume compared to sludge volume do we need to add given the sludge solids percentage. We're just talking about moisture percentage, so it's kind of flip it in your mind a little bit. If there's a lot of solids, you probably don't need too much wood chips. If there's just not very much solids and it's mostly soupy, you just add a lot of wood chips, right? We could design or there are designs out there for that type of deal. Okay, so I mentioned these aerated static piles. This is what they would look like. Again, this is sort of industrial scale. You're probably not going to do this in a developing context, but it might give us thoughts about how would we set something up to get the proper aeration. And I guess I should also mention, sometimes for like industrial processing, you may have an anaerobic digester first, where you let a lot of anaerobic processes occur. That's where you'd get your biogas. That'd be sort of the first step in treating your solids. That will help break a lot of molecules down into simpler components and allow for biological activity to proceed a little better in the future. Then you would pile your stacks of biosolids, something like this. Oftentimes they'll have some kind of a blanket type material that is permeable, will let air through, and then you'd be pulling air through these blankets, through a system, and discharging it out here after probably some sort of filter material to help with the odor and stuff. Catch your liquid losses on the way and just have a setup like that. So then you'd have a pile, it would be sitting there for some time, maybe you mix it. I think the aerated stack piles, they don't need mixing because you're pulling air through the whole thing. But you could also envision a situation where you had several piles and you just come and mix them every few days. and the one that's been sitting there the longest is the next one you take away to use, right? If this one has been here now 30 days, it's good to go. And you would just pile them up that way. Another possibility is in-vessel composting. You have some silo or some vessel, and maybe you're adding the waste to the top. It's very, very slowly flowing downwards in that sense, and you are injecting air to the bottom. And so by the time your solids make it to the bottom and get harvested, I think this, an outlet here. By the time it's there and you're extracting it, and maybe you're just sort of using like a screw propeller type thing to just pull the solids out. By the time it's there, it's been in there for X number of days, right? So there's several options, several designs you could make in that regard, and have everything working as you see fit. And again, this is sort of the industrial scale. In a more applied or developing scale, we saw at that farm they had they were probably the 55-gallon drums or close to it, plastic drums here that were sealed, and they were letting some anaerobic processes happen. And I think then they would later take that, and I don't know if they applied it directly or if they had some other steps probably to get it prepared to be mixed in with the soil. But they were definitely had some in process. The chicken manure, they had added molasses. And if you think back on, I was talking about the carbon, nitrogen, phosphorus, chicken manure would be very high in nitrogen and phosphorus and probably not enough carbon, which is why then you'd add molasses, which is mostly carbon, right, to get a good ratio there for the biological processes. Okay, some more designs possible as ways to collect it and all that. Okay, so coming back more directly to point of use stuff, if you are going to compost human waste, urine separation is a good idea for that nitrogen, phosphorus, carbon situation, and partly because urine's a lot easier to handle in terms of safety, in terms of applying it more directly. You don't have to compost that. So you'd probably use a toilet bowl that looks something like this, something like that, in order to redirect your urine versus your feces, and then you could use the urine accordingly. So maybe directly as a fertilizer, maybe have some sort of a soak pit to take care of it just separately. In general, this is going to help if you're using a latrine. So this probably does not apply to a full running water scenario, right? Full running water, we'd have to do things a little different. But for a non-flush toilet, if you separate your urine, then suddenly your fecal matter has much less water content. So that would immediately improve the starting point. Okay, and that's kind of why we see it in this picture, that we have that separate line to go somewhere else. Okay, I found a few interesting kind of alternate ideas, and you can see some old pictures here. This looks to me like somebody that's well educated and fairly rich out in the middle of nowhere, wanting to live an off-the-grid sort of life. So that would be the type of person that maybe would be interested in composting their own waste and would have the education where it might be appropriate, right? So not necessarily for every condition, but you see here what they've done is they have a solar system where they have a nice solar window here and probably some reflectors to help heat a composting bin. So solar composting latrine is a potential option. You have to make sure you're ventilating it well, and you do see pretty good ventilation on this system. And I think this is a window down into a pit, under here, right? So the point here is making use of solar energy to help drive up that heat and get your compost where you need it to be. Another schematic of that type of a system might look like this, where you have your toilet, and then you essentially have a rotating collection thing where You will collect waste in one bin for a little while until it's about full, and then you rotate it, and your compost now, is being heated by your solar system, and you're filling in a fresh new bin. You're exhausting all of this well, of course. That will help with some aeration, and you probably have to stir the stuff every once in a while. So, going to be a dirty job. But do all that. You may have some decent compost material that is not a terrible thing to use and apply somewhere. So this would be your carousel composting solar latrine. Could do it a little more simply. This may be actually what the pictures looked a little more like. You got the sun shining in, heating up your compost area. Again, you're going to have to stir it somehow, right? That's just not really getting around that. And if you're off the grid, you're probably not automating that too much. Automation might be handy. It might be neat, but okay. So there's a couple of links we can watch. One is about biogas production, kind of on the front side of a solids digestion. So I can play that in a minute. It's this old, like, poorly animated video, but it's kind of funny and informative. So I'll play that in a minute, but first we'll go to this autarky. Let's see if the sound will be good. Okay. This is just 4 minutes, them showing the system here. I think it might be in another language, so there's probably subtitles.
Und als Drittelement haben wir Handwaschbecken mit recyceltem Grauwasser, wo wir sich laufen, weil wir dann Hand verwaschen. Nachgebrannte Sache vom Urin, hier wir hier noch Spielwasser für den Feststoff trennen. Das Wasser fließt rein, wird durch Schleuderkraft wieder rausgedruckt und in den Abwassertank gesammelt. Und Feststoff fallen direkt in der grauen Fäkalien an. Gerade nebendran sieht man der erste Schritt von der Urinbehandlung, die sogenannte Stabilisierung. Oben sehen wir stabilisierte Urinzahlen und das Wissen ist Calciumhydroxid, wo wir zum Stabilisieren liegen. Der Tank wird regelmäßig durchmischt. Das Ziel von der Stabilisierung ist, dass wir einerseits Krankheitserreger abtöten und andererseits verhindern, dass Nährstoffe verloren sind. Das ist der zweite Teil der Urinbehandlung. Da sehen wir den Verdunstungsreaktor. Da wird die heiße Luft angesucht und verdunstet das Wasser im Urin. Der Urin fließt auf die Tabelle. So sieht es mit frischem Urin aus, bis er trocken ist. Dann kann man ihn abkratzen. Und am Schluss haben wir ein Nährstoffkonzentrat, ein trockenes, so in der Landwirtschaft als Übergang. Wir kommen zur Wasserbehandlung. Was wir so haben, ist ein geschlossener Wasserkreislauf. Im ersten Teil wird Wasser biologisch behandelt, fließt dann durch die Ultrafiltrationsmembrane und wird aufgepumpt, oben links in der Aktivkohlefilter. Nach dem Aktivkohlefilter geht es in der letzten Teil der Behandlung. Jetzt sehen wir oben eine Elektrolysezelle. Die produziert eigentlich laufend ein bisschen Chlor. wo das Wasser desinfiziert, so müssen wir das Wasser zum Handwaschen und zum Spielen sicher wiederverwenden kann.
Das ist der Vorlagetank, in dem die Fäkalien gelagert werden. Mache ich mal zu, weil es ziemlich stinkt. Und dann werden die Fäkalien aus dem Tank mit der Zahackerpumpe in einen Bereich geführt, wo sie zwischengelagert werden. Dann werden sie mit Luft beaufschlagt und dann wird das Ventil zum Reaktor geöffnet. Das heißt, die Luft schießt dann die Fäkalien in den heißen Reaktor und dann findet die Reaktion statt. Das ist eine Verbrennung. Die Temperatur, die da drin herrschen, sind zwischen 400 und 600 Grad Celsius und der Druck liegt ungefähr bei 300 Grad. Nach einer gewissen Zeit, wenn die Reaktion abgeschlossen ist, wird das Ventil am Ende vom Reaktor geöffnet und die Produkte werden in den Phasenseparator oder Kondensator eingelassen. Und das Produkt, das dann rauskommt, in dem Fall sieht so aus. Also wir haben da die Flüssigkeit und die Asche, die sich schon am Boden abgesetzt
All right, yeah, I'm glad to see some of you were concerned about the gloves, right? Lab safety and all. Yeah. Thankfully, she had hand washing station right there, right?
Yeah.
With super clean gray water.
The water running out.
Yeah. So I don't know why this is not a link here. Oops. Okay, let me grab this. So interesting, right? And I think that's certainly not directly applicable to most scenarios because, in incineration and high pressure, all that, there's a lot going on there that would not necessarily be accessible to your typical person, right? I have seen incineration toilets in the States even. There was once visited a boathouse that had one as a way to deal with their waste. So it's something that some places do use or do have, but not the most typical. Okay. So we also have this video here. Like I said, it's a bit dated, but it does show a neat kind of overview of this, in this case, like agricultural, kind of industrial scale. We would call it, in the field, we call it a CAFO, concentrated animal feeding operation. So CAFO, CAFO. And so if you get a bunch of manure from something like that, you have a whole lot of organic waste, a whole lot of nutrients to potentially recycle, and a big potential to harvest that waste and stuff. So this would be putting it at a big scale and kind of see what they're dealing with from there.
Welcome to a virtual tour through one bioconstruct biogas. Controlled fermentation of biomass in biogas plants produces a gas that can be used to produce electrical thermal energy on account of its high percentage of methane. The raw materials used in biogas plants, also known as substrates, are often liquid manure, agricultural products, and agro-industrial waste. The following animation will demonstrate how electricity and heat are produced from these substrates in biogas plants made by bioconstruct. This biogas plant uses inside its maize as one of its renewable raw materials. With the aid of a wheel loader, the maize is tipped into a cement storage bin, which needs filling up approximately once a day. Silo maize is rich in energy, and on account of its high degree of production, very well suited for use This storage bin is equipped with a hydraulic floor capsule that continuously feeds the maize onto a conveyor.
So that would be your bulking agent.
Wait the maize side. Equipping your is the most important basic substrate using this biogas tank. After poured into and storage in the big size, it is not supplied directly into the blending pump beside the maize conveyor belt. At the same time, the maize falls off the conveyor belt into the separator, which is equipped with two mixing rows. In this way, the maize silage is mixed before fermentation. With this technology, it is possible to supply several fermentation tanks, also known as fermenters, with the fresh substrate, even if they are not close together. Liquid waste from the food industry is the third substrate used in this tank. As the availability of such waste varies considerably, a large storage pit would be used. Integrating this into the wall serves to minimize smells and to help prevent epidemics. Now the liquid waste is heated with hot water to 70 degrees centigrade in a tubular heat exchanger using a countercurrent process. After heating for 1 hour, the hydrogenization of the substrate is complete so that they can now also be poured into the fermenter. Here is where the biogas is formed. The substrates are continuously stirred in order to prevent layers of material forming at the top or on the bottom. A hot water wall heater heats the substrate between 35 and 55 degrees centigrade in order to accelerate the formation of methane. On average, the substrate is in the fermenter for a period of around 30 days before it is filled into another fermenter for a further 30 days to complete the gas formation process. When fermentation is complete, the thin liquid substrate is pumped into 2 reinforced concrete tanks, where it is stored until it can be brought out onto the field. If the fermenters are filled regularly with biogas, are airtight, heated, and regularly stirred, the biogas forms within a matter of days. The formation of gas is a complex and delicate process. The organic fats or carbohydrates contained in the substrate are digested by various kinds of bacteria, and this is the starting point for the development of gas. The contents are continually stirred, the gas rises slowly to the top of the container.
Pretty amazing little bacteria.
And also,
The animations.
You
need little plushies like those.
The gas is first freed from water vapor, colored blue. The condensation water is collected and condensation fat and passed. The aggressive trace gas hydrogen sulfide is now extracted from the biogas in a biological desulfurization plant. By introducing air into the condensation, certain bacteria cultures are able to establish colonies on the chain. Here they decompose hydrogen sulfide into harmless sulfur. The almost unpressurized biogas is then fed into a compressor, where it is brought up to the 70 millibar pressure later required for burning. In order to completely condense and eliminate water vapor, freed biogas and suspended matter or silicon, biogas is subjected to a washing drying process. This is carried out with a vapor of almost freezing point, so that the gas is cooled down to a temperature of under 5%. In order to control the purification of the gas, the biogas is constantly tested with an online metric system, which records the amount of methane, hydrogen sulfide, carbon dioxide, and oxygen. This gas is with a high degree of thickness and In case of any overproduction of biogas, it is necessary to operate a gas flare or unburned methane that escapes into the atmosphere is harmful to the climate. The biogas-free biogas plant enables two gas heating generated power stations to run and be CO2 neutral. To annually process biogas from 15,000 tons of biomass, this plant must produce a total of 500 kilowatts of electricity. Due to the optimal gas processing, the end user can run itself in several years with only a minimum of up to 30% of the waste heat to the cooling water of the engine is used for the heat exchanger of the fermenter, so that no additional heat is required. The remaining heat can also be used profitably to heat industrial plants, houses, or swimming pools. The electric power generated by the generator of the block heating and generating plant is converted to the main voltage generator transformer. Then the electricity can be fed into the grid to meet the annual.
Okay, so I think that's about it. They go a little into the automation and stuff. So you can see that, I mean, that's a super fancy version, you know, fancier than regular composting. And their whole system there is actually more so on the biogas production. Their result will have a solids fraction that they can use. They might need to dewater it a little bit more, but it had already been through the 70 degrees Celsius for a short amount of time and fermentation at pretty high temperature, all that. So it's probably already class A solids. I'm not exactly sure in that scenario, but that's like the highest tech level of taking a really high concentrated manure stream essentially. And I think the rice husks there or something, maybe that was actually just a carbon additive. If they're flowing all this, it would still have to be pretty fine. So maybe that's not truly bulking. I'm not sure. Or maybe that was the manure and I just mistook it. At any rate, that's kind of an example. Next time you see composting, you'll maybe have a little more appreciation for what needs to be going on to make that safe. And if you're just composting in your, on your back porch, in your yard or whatever, you might recognize that, yeah, some of these biological processes are going to take a little while. If you give it conditions right and a good consistency and enough moisture, the stuff should end up getting a little warm and be doing a lot of processes, and it's good for it to stir it, keep it somewhat aerated in that sense, and it will transform the stuff. When I was growing up, my mom did some composting, so it's a while ago, but I remember it was a little stinky sometimes, but it would really transform the stuff. You get some worms growing in there or whatever, and you get like turned into soil from like banana peels and whatnot. It's some like stuff happening there. So just wanted to kind of give that that sort of a big picture, what it's like industrial scale, what that might look like without all the super infrastructure. Certainly something possible. And at the end of the day, pathogens, fecal oral route of transmission is kind of the primary concern. How do we prevent that? How do we deal with that? So, all right, that's all I've got for you today. I'll see you on Thursday.